Hi, today I wanted to talk about the radial basis functions and the way it was used and implemented inside of the verb and adverb paper. And I've done it in a separate video because the mathematics behind the way they've used it and how they computed it is quite complex, and I don't want it to make the video about the paper itself too long. So this one we just talk about the radial basis functions in the approximations and blending sense of the paper and nothing else. The first thing I would do is import all the libraries I would need. And then what the paper does is that they said that they have a bunch of adverbs, and basically an adverb is a style or anything in that way inside of an animation. So it could be the mood, the style, or turning left, leaning right, all that kind of stuff. So all of that is adverbs for which you can try to blend between different values. And then all those adverbs would drive all the degrees of freedom. So for them, it would be the rotations and the translations of every bones. So the elbow, the 1 degree of freedom, the 2 degree of freedoms of the wrist, and all that kind of stuff. I would make this a little more simple in this video so I can actually visualize what I'm doing. So what I would do is that I will have the adverbs will just be left, right, top, bottom inside of a 2D grid. And my degrees of freedom would just be a color. So I will have 3 degrees of freedom, red, green, blue. So I have multidimensional inputs, multidimensional outputs as the paper, but something that I can visualize. So what we have is a bunch of points on the grid. And for each of those points, I will have the corresponding color. So what I have is this bunch of points on the grid and color for each point. And what I want to do is to be able to basically interpolate those values and having the color displayed along the entire square. To make things a bit more interesting, instead of just doing basically 2 adverbs that are really what they are, it's left, right, and top, bottom, I'll turn them into 4 different adverbs, all just positive. So I will have the right, the left, the top, and the bottom as separate adverbs instead of just negative and positive. It will give you the exact same interpolations, the exact same values either way. It's just that in this case, I have a higher dimensional inputs, which it will be interesting to see that you're not stuck to 2Ds or anything. So I will turn those coordinates into adverbs, and those adverbs now are 4-dimensional. So each points now, so you get left, 0 left, of course, right, 0.7, top and bottom for each point. And so I get a 4-dimensional adverb space. And what they would try to do is basically allow you to interpolate those values. I've rewritten the mathematics as the way they use it, except that I will use the names of what I'm representing and not the degrees of freedom, all that kind of stuff. So basically what I have is an interpolated color, which is why I have the little C here, because it's 1 degree of freedom inside of the color. So C would be red, green, or blue. So the interpreted value of one specific point, and remember that point is inside of the adverb space, so left, right, top, bottom. So it's a 4D point. It would be the sum of the radial coefficients multiplied by the radial basis functions, the same way we're doing radial basis functions usually. So it's the radial basis functions for a specific point, multiply for the weights, and then see, because I'm multidimensional now, I have a weight per example, the little I, and per color. So I will have, in my case, I have 7 points and I get 3 colors, so I get 21 different weights in this case. And on top of that, you add a linear approximations of the interpolations, and that the way of doing it. This is now it's per adverbs. What you will have is a coefficient, a linear coefficient per color, per adverbs, and it goes through the linear functions instead of the radial basis one. This is fairly similar to the way we were doing in radial basis functions, where we had a polynomial constraint. We added a bunch of constraints, and to do this we built a matrix. When you remember, we had 1 and then x squared, x cubed, and so on, depending on the degrees of freedom of your polynomial. Here will be the same. What you try to do is to find, for all the points in our 4D space, we try to find a hyperplane that will best approximate all those points. So that's what this tries to do, tries to find an hyperplane that goes through all the points and approximate as best as you can do. It's basically a linear regression. And to do this, we would do the same kind of system that what we did in the radial basis functions. I will actually put a 1, and then instead of doing x squared and so on, I will basically do 1 and then adverb 1, adverb 2, adverb 3, adverb 4. I get 4 dimensions. So it's 1, left, right, top, bottom. So, and I do this for every point I will have, and that gives me a big matrix with a bunch of 1s, all the values for the, all those values here for the left, all those values here for the right, and so on and so on. And then I can try to solve for the actual coefficients. Except that, of course, you don't have a real answer. I cannot just do inverse matrix and solve as we did when we were doing the radial basis functions. Now what I have to do is to go through a least square to find the best approximations. So this is exactly what I would do here. What I have is the adverb matrix. What I do is that I compute the 1s and then all my adverbs, and then after that I do a linear least square, so I can find the best solutions, and that gives me these coefficients. And it gives me the coefficients for all my degrees of freedom, so all my colors at once. So basically what I have is the red, the green, and the blue, so 1 for each values, and I get the 5 different coefficients, and the 5 coefficients is the coefficients for the 1, and then for left, top, left, right, top, bottom. So I get 5, and I get 3 values here. The idea behind this is I could have solved for one color at a time. I could have solved only for the red, then the green, then the blue. It will have given me the same answer. It's just that I can compute the multidimensional in one go inside of NumPy. So that's how all my linear interpolations is working. Now, what I would have is I can display the interpolated linear approximations. So what I'll do is I make a big grid of 40 points, and 40 points I get 1600 points for which I have all the coordinates. And I would turn that into my adverb space, because I'm not interested in coordinates again. I'm still interested in blending different adverbs together. So I'll turn that into my 4-dimensional adverbs. And then I create the interpolations adverb data the same way. And then I can just multiply my matrix together, and that gives me the color. So what I will have is this. So the linear approximations give me this. It's the best color I can find with linear approximations. So that's what you have here. Now what we want to do is to get something a little better than just that linear approximations. What we want is to be able to get the exact values here. And that's why now we need to use the radial basis functions on top of what we've done. And the way we would do this is we would compute the residual, so the amount of error the linear approximation is giving for each point. And so we take the real values I have, and I will subtract the linear approximations, and that gives me the residual, so the amount of error the linear approximations gave me. And so this is the residual it gives me for every point So my 7 points, and for the red, the green, and the blue again. And now that's the residual values that we will go and plug inside of the radial basis functions. If you remember what we did the radial basis functions, what we had is a kernel that turns any distance into values that goes between some parameters, some values, depending on the type of kernel you want to use. And we had to use the Gaussian kernel. What they used inside of this paper is the dilated cubic B-spline. The cubic B-spline curve is something we've already seen when we were doing the videos for the cubic B-spline, and it's the same formula. So I will use alpha of that B-spline, cubic B-spline, as these functions, and I can display what it looks like if you remember. So it's split into two functions that stick together, and the advantage of the cubic B-spline like this is that it has a radius of 2, and anything that is further away than 2 is just zeros. So you get a nice curve, and then at 2, further than 2, everything is zeros. So now that's the kernel they would use. So what they could do is that basically say, as I said, you get all that. If you remember how to solve for the radial basis functions, we build that big matrix with a distance between each point and each point, and then we multiply that with the weights and equal our values, and we solve for that system to find all those weights. Except that what we have here is that we don't solve for the values itself, we solve for the residual, so the amount of error the approximations, the linear approximations gave us. And then the distance is where it's a bit different that the radial basis functions, where we were just giving the Gaussian kernel and the same distance, the same way of computing a distance for each of them. What they said that the D is built this way. And what it means, it's actually, it just means that it goes through the Bézier, the cubic Bézier. But what you feed inside of the cubic Bézier is the distance of the points. So that's R, I1 is the distance between your points and the example, divided by an alpha. And what the alpha represents, it's basically the distance of all the closest points. So what they really want to do is to make sure that they will only do radial basis functions with all the values that are fairly close to the points we have, and anything that is too far away inside of our approximations is not used. And basically to do this, what I said is that for every point, you check all the points, all the other points when you build that matrix. You compute the distance for all the different points. And then you take the closest distance, and then you divide all the points, all the distance you divide by that one. Which means that basically what you have is that the closest point has a distance of 1, and then everything else will be a bit further away, and everything that is actually at a distance of 2 or more has no influence. So it means that you only have values that are fairly close to you that are used inside the radial basis functions, and everything that is further away is discarded and not used. So you don't have weird interpolations of pose that are really far from each other, influencing each other. So what they have here in this case is really that everything that is close has an influence, everything further away has no influence. So again, I will compute the distance as we did earlier, except that this time it's for the Euler distance. So I compute the distance between every point and every point, and it'll give me this matrix, again with in diagonals all the zeros, because point with itself is a distance of zeros. And then I can compute those alphas for each point. Basically what I do is that I go through every row and I try to find the minimal values I have inside of that row, which is not 0. And that will give me the alpha by which I need to divide all those values for each column, basically to give me the proper values scaled. And now that I have the alpha, I can take the distance and I can divide those distance by the alpha. And basically what it gives you now is a matrix where, you know, the zeros are still zeros, and then the smallest values I had became 1, and everything is bigger than 1. So you get 0, 1, and then something a little bigger than 1. So all of those have influence. And I know that everything that is past 2 will have 0 influence in my radial basis functions. So not all those will have influence, but this one has the most influence, and then everything else a bit less, and everything that reached 2 has no influence. So I get a bunch of values will be discarded when we will be computing the radial basis functions. Now that I have those scaled distance, I can make them go through the kernel itself, and that gives me now this distance now for all my different coefficients. And again, exactly the same way we did in the radial basis functions. Now I have my matrix of distances, I get my matrix of values, I can solve to get the coefficients, and I get the coefficients now here for my 7 points. And again, I'm computing every degrees of freedom at once in those matrices, so I get the values for all the reds, the green, and the blues at once. And I can easily display now the final results. It's basically, as the functions we're doing on the top, is you add the linear interpolations you did, and then you add the radial basis functions together. And when you do this, you get these interpolations, and now you can see that we have something fairly neat when my inputs are not that visible anymore. So all of that has been properly interpolated. Now, it's tricky to understand why it was done this way. Basically, the advantage of doing it this way is that the linear approximations give you an opportunity to do extrapolations. If you remember, radial basis functions are really bad at extrapolating, but the linear interpolations is just, it's fairly bad anyway, but it can give you extrapolations. So the linear approximations allows you to have extrapolations, and then the radial basis functions is only looking at poses that are fairly close to the examples, so it's avoiding having influences from poses that's far away when you have really scattered data. So that's the reason why they've split it into you have an approximations that is not too bad when there is no data, and they can give you extrapolations, and then the interpolations when you have data, which is fairly good. What I will do now is just for the paper itself. So I would turn all the code that I have here into a big class so I can reuse and recall. And basically, it's just all the functions we had. I get my base here that is defined here. I get the initializations where you will give all your points and adverbs as inputs when you init the radial basis functions, and I will pre-compute everything that can be pre-computed. So the D for the distances, the linear adverbs, the alphas, all of that is stored and saved. And then you can fit your data through that radial basis functions. So basically, is the step when you actually compute the coefficients, the real coefficients you want to use. So you can fit, and it will return the linear coefficients for your data and the radial coefficients for your data. And then you can call the radial basis functions to do the interpolations. And then what you do is that you give him the linear coefficients you had received, the radial coefficients you had received, and the points or the point or the points you want to interpolate to get the interpolations. Why have I split it in two different functions like this one? It's basically, even if all my adverbs are defined in advance, because I would know what the adverbs I want to use, I can fit different type of curves. I can fit all my degrees of freedom, or I can fit only one, or depending on how I want to use these functions, I can reuse the same adverbs with different input data, and that will be useful for the paper. So that's why I split it into this way. And then we can see that it actually works. So if I do the color again, I'm just doing the RBF, giving the adverbs, then I fit my data, and then I try to interpolate with all the data points interpolations, and then that's it. You have it. All that code now is just 3 lines here, and it works with any dimensions. So in this case, have 4 dimensions adverbs and 3 degrees of freedom. I can do it in 1D as we were doing before. So I get 1-dimensional input, 1-dimensional output, and that's the interpolations they will give me. See, it's not perfect. If I was doing a pure radial basis function, they would give me a better answer than this one. But in this, you could see that it did the linear interpolations as best as it could, and then it did the interpolation in between. So that's the implementations of the radial basis part of the paper. I'll see you in the actual paper analysis to see how this is used and how it can be used to blend animations together and how it was done. See you in the next video.